In this video, we'll look at a first-order linear problem, which is also an initial value problem. The differential equation says y prime is equal to 10 minus y over 5 minus t. So y is the function, and t is the independent variable. It's supposed to satisfy this initial value at t equal to 4, y is equal to 0. Notice that t cannot be equal to 5. And as a consequence of that, we're only going to be able to solve on a particular interval. Either t should be less than 5 or t should be bigger than 5. And we'll choose to work when t is less than 5 because our initial value is t equal to 4. So it's clearly linear. I'm not doing anything to the derivative or y itself other than involving some coefficients that involve only t. I'm not squaring y or its derivative. I'm not cubing it, taking square roots of it, or mixing it up into more complicated functions. So in order to solve a first-order linear, we should get it into standard form. In this case, I should get the coefficient of y prime to be 1, move the y term over to the left, and move any terms involving just t or anything else over to the right side. In this case, I need to move the term here over to the left side, and I'll leave the constant on the right. So my p of t, my coefficient of y, is 1 over 5 minus t. My integrating factor then, mu, will be the integral of p of t, and then use that as the exponent for power of e. So we need to integrate p of t first. This is a logarithmic form. Be careful here because it's minus t. I have to take 5 minus t log of that, but the chain rule, if I differentiate, would give me a minus sign, and I don't want that extra minus sign, so I'm going to put 1 in front of it to cancel that out. I don't need a constant of integration here because I'm looking for any integrating factor, and we'll take c to be 0. Notice I don't even need the absolute value here. If 5 minus t is always going to be positive when t is less than 5. So I can now take mu to be e to my integral that I just calculated. Notice that minus sign I want to get out of the way so that I can use the properties of logs and exponential functions here. So I'm going to use it as a power now. It's going to be 5 minus t to the minus 1. And that, when I apply my properties of logs, will be 5 minus t to the minus 1, and that's really just 1 over 5 minus t. So we multiply through by the integrating factor mu. Everything in the original differential equation here, first term gets multiplied by it, second term gets multiplied by it, and now it's going to be squared. And then don't forget to do it on the right-hand side as well. If you've done everything right, that left-hand side will be a derivative of a product. And it should be your integrating factor times y. Let's take the time to double check. If I differentiate y, there it is, and I leave the rational part alone. If I differentiate the rational part now, you'll get 1 over 5 minus t squared, and the negative 1 power sign will cancel with the negative 1 from differentiating using the chain rule here. The y will leave alone, and that's equal to 10 over 5 minus t. We now integrate both sides. On the left-hand side, we get what we were differentiating back. On the right-hand side, we'll have to carry out that integral, and effectively the same as what we just did. Again, don't forget that minus sign that comes from the chain rule. And we solve for y by, in this case, multiplying both sides by 5 minus t. So I'm going to multiply over here by 5 minus t. There's my minus 5 minus t times the antiderivative that we just did. And again, don't forget to multiply that by the constant of integration as well. Otherwise, you'd be losing a term in the solution. There are general solutions to the differential equation, but we have an initial value, so we should use that to find the specific solution that we're looking for. So y is equal to 0 when t is equal to 4. Let's plug that in. I have 0 for y, and I'm going to plug 4 in, so it'll be minus 10 times there, and then it'll be 1 there, natural log of 1, And then don't forget to evaluate here as well, and we'll get c times 1. And if you simplify, log of 1 is 0, so this term's 0, and we get c must be equal to 0 itself. And that means that the specific solution that we're looking for just involves this first term and doesn't involve, after all, the constant term. Simplifying a little bit by distributing the minus 10 through, we get that expression. That's the specific solution to the initial value problem that works on the interval t less than 5.